Way ANOVA, we're going to look at what we call either a two-way ANOVA or a factorial ANOVA. We use the names interchangeably. So in a two-way or factorial ANOVA, the key difference is I can actually group students in two ways. So for instance, I could say I want to look at if the academic track a student is in affects their math achievement scores. That's one grouping variable. And I also want to see if their math grade, if there's a difference when I look at them by math grade, if there's a difference in their math achievement score. Because those are two grouping variables, because the math grade and the academic track are going to be two separate groupings, then that was what makes it a two-way ANOVA. So I want to first figure out what on earth is math grade. And so math grade only has two groups. It has less than an A to a B or most an A to a B. So we're just breaking students up basically by a high score versus a low score is what we're doing here. Academic track, we know from earlier analysis, is just a fast track or a regular track, which is like an honors versus academic course. So this time, instead of just trying to determine if there's a significant difference between students on fast track and academic track, I want to see if there's a significant difference between the academic tracks and between the grades. Because I have two separate groupings, that's going to become two separate hypotheses. I also have, I can write the research question as one research question, or I could break it up. But typically, I personally, when I work with students, I prefer one research question, and then you can break the hypothesis out better. So I would say, is there a statistically significant difference on math achievement between students who have a high or low math grade or students who are in the fast track or academic track? So you see how I'm just switching around like that between, I have an or. So I'm looking at low score, high score for grades, or fast track and academic track. So to do the ANOVA itself, it's pretty straightforward. You're going to go to Analyze like we typically do. We're going to go to General Linear Model. We're not going to go to Compare Means. So if you're looking in Compare Means, you're not going to find the factorial ANOVA. We're going to go to General Linear Model, and then we're going to take a look at the univariate section. So basically, it doesn't ever say two-way ANOVA, which does make this a little bit less intuitive. So I want to move math achievement into the dependent variable. Why is it a dependent variable? Because I'm trying to see if academic track or the grade in the math course impacts math achievement. So what I'm trying to say is that math achievement would depend on the academic track students in and their grade and math score. We're not really going to touch this random factor, covariate, etc. We're going to work in fixed factors. So in fixed factors, I want to move the academic track and math grades in there, so that now I can check for two different factors that I'm grouping with. Once I'm in here, I can adjust and make some different options. So I could actually say, I want you to create a plot for me. Like, I want to see this visually and not just in a table. If you wanted to do that, then you could take math grades and move it over to the horizontal axis. And then you could take academic track and move that to this separate lines box. So basically what I'm telling the software is, I want to see a visual of math grades, but I also want to see academic track on a separate piece. So that way I have two different graphs of both of my grouping variables. Then if I wanted to say, hey, what plot am I going to make? I can actually do that in this window. I could also do that using the chart analysis method we did at the start of the course. So this is really just kind of extra flair for if you want to create a chart at the same time that you're doing an ANOVA. You definitely don't have to do this step, but I'm just showing you that it's possible to do it in this menu versus going to the chart analysis. In the options area, I also have a couple of different things here. I need to always check off descriptive statistics, and I'm going to check off the effect size because we're going to report out the effect size for the two-way ANOVA. Significance level for us is typically going to be 0.05 because we are in education and that's the consider it 1. This is going to be exactly like when we worked with the one-way ANOVA where these boxes will become unchecked, and that can be kind of a problem. So you want to make sure every time you do the two-way ANOVA, you're going to click options, you're going to select descriptive statistics, and you're going to select the effect size. So those are two different pieces that we have to actually do. We are not going to select the homogeneity test. So we don't need to know about the homogeneity for a two-way ANOVA. We're actually not going to report that out, which may feel weird because we've been talking about Levine's test a lot, but with the two-way, we're not interested in the variances. So I get back to this menu. I have everything fully set. If I wanted to run a post hoc test, I can definitely run a post hoc test. You're not going to see that until 8:35. So there are some post hoc tests that I can definitely do with the two-way ANOVA, but I'm not going to do those in 8:10. Those would be what would happen into the further piece. So I've got everything selected, and I'm going to click OK, and I'm going to see where this brings me. So I have lots of output. I have my between subject effects. I have my descriptive statistics. I have my test between subject effects. And then I have my line plots that I created. So again, we're not going to touch a post hoc test until we know what's going on in the two-way ANOVA. So there is a post hoc test system available in the ANOVA, but we wouldn't touch it just like in the one-way ANOVA until we're all the way at the end. So if I'm looking at all of this data, I can start to glean some interesting information. So we're going to leave the descriptives alone, and we're really just going to live here at this between subject effects. And we're going to look at the line plot that we have. So if I'm looking at this between subject effects, you'll see there's a whole lot of significant values on this table. And it's kind of weird because you've got this corrected model, you've got this intercept here, and then you actually see the variables that you had. You see academic track, math grade, and then academic track with math grade. So what I am looking at is just the variables that I grouped by. So that would be here, these three values. So you want to locate what you're grouping by in the table, and those are the significant values that you look at. So if I'm looking at these significant values, that's going to tell me if there's a statistically significant difference. So if I look at this, if I look at academic track and math grades, I'm going to reject the null hypothesis for both of them. So I know that there is a statistically significant difference in academic track and math grades. Now, when I combine them and I try to work with them together in this third row, that's not as telling. That jumps up to 0.563. And so if I'm looking at it as 0.563, that's not statistically significant. So that's looking at math grade and academic track interacting simultaneously. And it would not be significant if they're interacting simultaneously, which is interesting. It's kind of a weird thing for us with the two-way ANOVA, but it happens. There's also some other additional information that I can take away from this. I can look at this adjusted R squared of 0.216. What that value means is that's the percentage of variance in math achievement that's predicted by academic track and math grades. So 21.6% of their math achievement score is explained by what academic track they're in and what their math grade is. So that's interesting with this piece. Then we have this column with eta squared. And so you'll want to look up in the index of your math book and look at eta squared. And eta squared is the effect size for each of these variables and the interaction. So if I look at this If I look at this, the effect size for academic track is 0.163. So about 16.3% of the variance in math achievement can be predicted by academic track. Same thing here for math grades. About 17.2% of the variance in math achievement can be predicted by their math grade. And so that's what that partial eta squared piece is telling us. Then we have these plots, and I just kind of created a plot so that we could take a look at what it looks like visually. And if I look at fast track students, it's pretty obvious that they left everybody in the dust. If I look at the lines, they do appear to be kind of parallel, but there's a significantly big jump from regular track over to fast track. So that's just interesting, and that gives people a visual, because it's how do I interpret math grades and how do I interpret that with the academic track and the fast track. So students who are in fast track have mostly A to B's, and then when I'm in the academic track, I have more A to B's than I have less than A to B's, which is kind of a nice indicator. So this plot is kind of extra piece to do. It's a visual for visual learners, but really you're going to live in these tables. And so if I wanted to report out a post hoc test, I'm just going to show this to you so you can see it. If I go to analyze, then I'm going to not go to compare means. I'm going to go to general linear model, and then I can actually access all of my post hoc tests here. So let's say that I found that math grades is significant. I would be able to follow my flow chart for the one-way ANOVA and know which one that I need to do. I'm able to check it off and see if I'm going to use two keys or if I'm going to use something else here. And it has its own flow chart that we're going to kind of build on in 835, but I think it's really important to show you that it is possible, and you'll notice that in this area, things are grayed out. So you can't get to equal variances not assumed because you're not able to run that for this test. So that's why we're not checking Levine's. So in that way, the two-way ANOVA is more straightforward. It is possible to calculate a post hoc test, and you can create line graphs or bar charts in the same window so that you don't have to go to Analyze Chart Builder.